Okay, seeing CE495, we're gonna move on to next step. Assume we complete the column design, right? The still column design, so column size should be vary. So just watch previous video, but you see the column size 14 by 342, per floor 311. So gradually reduce based upon their actual design demands, which most likely 1.4 dead loads or 1.2 plus 1.6 live load will be the governing load combination for gravity columns. So now I think just try to remind you that what we just complete the defining a new wall thickness and then define the material properties. I think our concrete strengths we initially set up, right? Default was a C4, but we created C5, C6, C7, C9, which actually we adjust our Young modulus E value, elasticity, right? So this model with various wall thickness, I think our wall thickness we use 24-inch thick with the concrete strength 9, goes down 22, 20, 18. So those are some the wall thickness we use with concrete strengths, various concrete strengths. So the one thing I want you to make sure is that again, the current ETABS version we adopt the new latest SCE7-16. They are using the ultimate wind loads. So when you define the wind speeds, which is 117 miles per hour, that is, you end up with ultimate wind load. So that is the wind load you're going to use for overall the strength design. But for deflections, again, deflection, right? Building deflection, similar to the beam deflection. We're using LIBRO deflection. We try to limit less than L over 360. Or total deflection that puts to LIBRO deflection, we're using kind of limit to L over 240, something like that. It's all based upon service load, which is no load factor on it. So in order to scale down ultimate wind load to service wind load, we're using 0.625 load factor, scale load factor. So wind load X has, this is ultimate wind load, but we apply multiply 1.625 to scale down to the service level, service wind load in X, both Y as well. So this is the load you're going to use for deflection check. So I'm going to just go open the display story response plot and maximum story drift, but I'm going to change to wind Y. I think end of the last video I show you current model, we had something deflections at the top, almost 21 inches. Our goal is total height divided by 400, which I think is about 16 inches. So we do need more lateral stiffness. All right, so at this point, I'm going to show you one thing and we'll move on. So let me see which section is most kind of clear to show. So now what you're going to do, what we see is wall and column. So it's a straight column load takedown is happening. As you're aware, though the column reaction is gradually increased. Gradually increase, everything is compression based upon dead load. Even though 1.2 dead plus 1.6 live load, you see that everything is red, which is compression, which is common sense, right? Gravity, Earth is always pulled. Everything is downward. So all these columns experience compression. If you want to see the wall forces, we need to apply some pier label on each wall. Maybe I'll just gonna show you. So what we're gonna do, we need to kind of select the wall here and go to assign pier, assign shell, and pier label. We're gonna assign pier label. This one This model I may already have some. Let me check the peer label, which I might have show. Not show peer label. I don't have it. So I'm gonna select this, assign shell. I'm gonna name it as a peer 1 here, and then also I'm gonna select peer 2. So this is kind of the name peer assignments. Let me see, I think we have another. Let me see this. I'm gonna select this one, peer 3, and this side, because those are continued. So I'm gonna assign peer. I think we do have another. Okay, peer 5, and this one I'm gonna assign peer 6, something like that. May have to create more. 7, something like that. Yeah, just stop it for now. So basically, well, on this, so we need to, yes, I assigned the peer label. I just skip this. You guys maybe, if you're interested, do this. So what I'm gonna show you, the peer label. I'm gonna rerun it and show you one thing. So with the peer label, the ETAB's gonna collect all the resultant forces, right? As you see the column, experiencing gravity compression forces due to the gravity effect. Since we are using shell like wall elements, we need to assign this peer label on the wall so that we could turn on the actual force and also in frame and peer. So we're gonna just collect, ETAB's gonna collect all the resultant forces from area element. So you can see that here column experience 7,000 kips. This wall experience 5,700, 7,000, right? So something like that. But one thing I wanted to make sure, because we're gonna add additional stiffness, which is outrigger sooner or later. But at this initial model, there is no such a big horizontal deep beam member or truss between the wall and the column. So all the floor, right, the floor loads on the floor, which is dead load, self-weight, superimposed dead load, and live load, they're coming over down through the column. But now, since we still lack of lateral stiffness in short direction, y direction, we try to add the outrigger truss. Then we'll see that how this outrigger truss diagonal member is gonna interfere or pick up some gravity forces and dump it to the wall. So that's something we need to aware, and I'm gonna show you. So next step, first, take a look at the plan, your plan. Since we have a good kind of series, a pair of wall right there, right? So we may have a choice. Initially, we may be gonna provide some truss along this grid line B and E first. Whether that outrigger can handle, two outrigger can handle for lateral stiffness, then that is okay. Otherwise, we may add another pair. So outrigger truss might be the 2 or 4. So I'm gonna just draw the truss on the B line and E line. So I'm gonna go elevation and pick up the B line first. So right here. So typically the high-rise building needs that mechanical space, which may be middle height. I'm gonna choose the floor between 20 and 22. I'm gonna draw the truss element. So similar to auto select, let me see, maybe I can create auto select. Do I have a bracing? Okay, I'm gonna go to define section frame. Lateral column. Okay, I'm gonna copy this guy. So this one I'm gonna say auto brace. Basically, this size is quite significant, so I'm gonna use W14 size, but I keep this W14 145 to 500. So we need to design. So I create auto select properties by copying from lateral column. So I'm gonna change this property a brace. So truss obviously normally pin. So I just pick up the pin conditions. Then I'm gonna draw outrigger brace from here to here double story. I'm gonna assume that double story truss. Right? First, let's take a check the property. This button doesn't work. Check the section. So I draw. Let me just turn on the text high, bigger. Epic mode, the preference. Alright, make this bigger. So then I just throw out this W14 A brace member. Since this bracing, in order to work, I think basically this triangular shape truss has to be work together based upon this geometry. I think the bottom, or if you want, try bottom core, top core. I'm gonna just assign as well a brace because it's not gonna be a typical beam size. It's gonna be huge truss size. So I'm gonna draw these trusses at this level on the grid line B and story between 20 and 22. So go back to plan. This truss is located on the B. I'm gonna draw another truss on the E line. E. Either you can copy or you can draw. It's all up to you, but I'm gonna for now be cautiously draw same thing brace and using a brace and pin element and pin connection boundary condition simply support it. So I'm gonna draw truss here between 20 and 22. I'm gonna draw another bracing here. Again, I select this top and bottom hood member and assign the property to a brace. Right? Okay. So now I'm gonna run it. Just at this point, we only draw two outrigger truss on grid line B and grid line E. This is something based upon, it should be based upon yours model, so you can find out which grid is really lined up with your between your column and also wall, so that outrigger should be straight. All right, let's see. Okay, so here's the analysis. Maybe I should have done with the new file, but I can recreate it. So let's check the same thing, gravity actual forces based upon 1.2 dead, 1.6 live rope. So now see that what's happening here, right? Because it is trusses, bracing is pick up some gravity load here. Previously, this compression force is continuously growing, but now because of these sizes, right, bracing elements is holding it, right? So this holding back to the core wall, so that a lot of tension develop here, which means the less compression force going down. So with this model, obviously I think if you're using this current model, you have some kind of issue. Likely you're gonna underestimate your gravity forces on your column side, column design. Previously, you designed the column based upon only gravity loads, but now since you tie the column with the core wall with outrigger, these two columns, right, and the other side is not only gravity column. This is works also lateral column because it's contributed. So taking that actual forces due to the any lateral wind forces. So this is something now you have to aware how we're gonna just somehow kind of manage this column forces reduction due to the this bracing element. So let me just so for now, since we add this, let's check the deflections. I maybe have to create a few more example slides, but here display plot. Let's check how much this outrigger is contributed in wind Y service wind load. So you initially had a 21 inches, now it went down to 16 inches, right? So basically this outrigger is tying the column and work together with our wall. So the stiffness, which basically we gain some lateral stiffness, so that overall deflection reduced from 21 to about 17 or 16 inches. So I think what you need to do is just look at your plan and choose the kind of line of outrigger truss you want to edit. Basically, exterior column, and you put the truss in order to tie the column to concrete shear wall. All right, so I think you can manipulate and kind of you may have to consider or continue if you see that okay here the actual forces under the gravity force, right? So 1.2 that 1.6 live rope. You know what? Let me show you one thing that B line. So let's check how about under the wind load. Now we have a wind x y, right? This is ultimate wind load. So see that how this building behave because of the lateral wind load, which is wind blowing this direction, that the wind is blowing this, so that this outrigger truss is holding work like a deep beam, so interact with the wall, so that the windward side, the column is experiencing tension, uplift, but opposite side is experiencing compression, right? This is rocking because due to the wind load. We didn't combine our gravity loads with our wind load together. This is pure due to the wind. So you should really can guess because tension on the windward side, compression on leeward side. But when you combine, maybe we need to kind of also, let's see, maybe probably this one. See what kind of load combinations. Might be 5, 4, 3, 4 might be the next direction. So here, let's say 1.2 that 1.0 live load and 1 wind Y. I think the load combinations 5. Probably here, you maybe see that all the actual force is kind of distribution like this, but combined effect due to the gravity and lateral. Still, we have some kind of issue on our gravity loads because the bracing is holding up, then we are underestimate our actual forces, right? Which if we use this model as it is, obviously we may end up with to under design the column. So I think one thing that we need to design due to the gravity force, gravity load. We design the column based upon gravity load. Now include the wind effect, with combined effect, we really design one more time, make sure every column is working, but most likely those column tie with the through the outriggers, that column is not gonna work, so then typically we need to size up, increase the size based upon our wind effect. All right, and just quickly, since we have this kind of issue, let me just save as to version 2. So maybe it'll show you both. So what you're gonna do in order to avoid that type of interactions, so we try to run the construction sequence analysis, which first of all, I'm gonna grab. This is more high-rise if kind of consideration. I'm gonna select only bracing. See, I'm gonna assign the group, assign the group. Where is my eyes? Assign object. Okay, so assign object to group, right? So this is Outrigger. So I'm gonna add to the group. My group name. Oh, they make something. So this one, Outrigger. I make just add the what group add. Yes, add group. Oh, wait a minute. Okay, assign and assign object. Okay, here I'm gonna the bracing. I'm gonna assign to this Outrigger group, right? So I assign it. Let me see that. Right click. Yes, it's part of group 2. No, wait a minute. Group 2 groups. Oh yeah, it's in the Outrigger group, right? So I maybe happen to assign those bracing member to two groups. So what we're gonna do, we try to set up the here construction sequence analysis. I'm gonna activate it. This construction sequence analysis is gonna be applied to dead load, which is dead load and SDL. And SDL, yeah, not live load. So we're gonna run the construction sequence analysis for dead load effect both, right? But we're gonna just exclude this Outrigger bracings under current construction analysis so that we try to avoid those type of effect. So this is the load, another load cases we're gonna use for our total dead load effect. So I create it, and maybe I need to choose the combine number of story constructions in order to make construction sequence analysis running faster. I just assume that wheel construction is happening every 4 floors. So I'm gonna rerun that. So I'm gonna show you that the column reactions, actual forces under this dead load effect, which means dead load and superimposed dead load. I'm gonna just combine as one my dead load cases, but this is the dead load effect. We need to use it for our column design. So throughout all the load combinations, that and superimposed dead load cases going to be replaced with this construction sequence dead load. Try to avoid that's kind of bracing is holding up, so we avoid any the kind of actual force loss in our column. So all right, so let me put this ones and show the B line B. Gonna show all. So here I'll show you again. If you just run dead load, which is not this one, actual force, right? See that the compression force is coming down. You lose some compression forces because of this bracing is holding back and dump those loads to the wall. But STL as well, same thing. It's kind of straightforward, right? There's nothing special. But now I'm gonna just choose auto sequence analysis. Let's see. So this construction sequence analysis, we this ETABS recognize, we choose number of floors. Construction is 4, so they building the model and analyze it every 4th floor. Let me just go back 2, right? Move 3, right? So this is something kind of, as your building is built every floor, obviously the column at the bottom below the experiencing it, right? But it's cumulative. It's kind of just addition. But since this model, we select these outriggers, we define this outrigger as a part of group, right? We exclude these outriggers elements during the construction. So this is part of analysis tool. We try to avoid that outrigger construction will be delayed, right? So up down here, up. So then we assume that we're not going to install this outrigger truss, or we place it, but we don't tie this outrigger bracing completely, right? Just leave it as a kind of open connections. But after our construction is completed, we tie the bracing element, which means bolting, right? So that at the stage, this bracing is activated and holding some actual force. So since this order sequence analysis, we just exclude during the construction and tie this outrigger at the last minute. See the compression forces kind of again the gradual. It's similar to the model we didn't have this bracing element before. So this is model is just the model is more comprehensive, right? The 3D model that we address this sort of effect, the bracing effect by using construction sequence analysis. So we can simulate this model can address their gravity load distribution and also lateral load distribution. Again, this model, we can see that the actual forces due to the wind. So see the compression tensions. Extraction is usually you need to rotate and to get a look at the other direction. So I'm going to put this one right there, 3D. So I want you to first kind of update your model and also include your lateral deflection study, right? So if you happen to choose right some sizes, initial size, you may see that the kind of reduce the overall deflection. But you can design the bracing as well. You can select the object type bracing, right? And I'm gonna only show this. Basically, these elements, since we have all the load combinations, you can just go to design steel and run it and size. And somehow initially the size is W14 by 370. So we may same thing, do iterations. I need to check few stuff, but I'll just go verify the pass, select, and then rerun it. But I think I didn't run the design check for the column that tie with outriggers, but eventually we need to do it. So since this video is too getting long, I'm gonna stop here. Maybe I'm gonna move to the next video. Okay.